All right, 13.2, we're going to talk about the paired t-test. And these are hypotheses about, how hypothesis tests about dependent samples. Last time it was all about independent samples. Now we're talking about dependent samples. So let's remind ourselves, an independent sample is where two samples are selected where the makeup of one sample has no bearing on the makeup of the second sample. So that's what uniquely makes it independent. Dependent is where the samples are connected in some meaningful way, sometimes directly and sometimes indirectly. So a direct comparison, a direct dependency would be like a post and pre-test in medical testing. Like if I had a drug that lowered your blood pressure, I could take your blood pressure, then give you the test, and then take your blood pressure again and see if there's a difference between the blood pressure after the drug has been administered. And so that would be dependent samples because sample one is you and sample two is you, right? They're both you, right? So that would be kind of a direct dependency. You can see clearly that the experimental units are the same in both samples. Kind of an indirect dependency would be something like crashing a car. So let's say I wanted to test the average restraint system, the new restraint system and the old restraint system of, let's say, Ford Tauruses or Ford Focuses. And so I would crash 5 cars with the new and then crash 5 cars with the old and see which one had better restraining systems. Now, obviously you can't retest a crashed car, and so we would say they're dependent because they're all Ford Tauruses made out of the same manufacturer. So we can make indirect dependency in that particular case. So most of the time, I think AP does a pretty good job of making it so it's clearly independent or clearly dependent for you to make your decision on what to do in these cases. So when it is dependent, like everything in this example, you're going to do what's called a paired sample. All right, it's a type of dependent sample where the observations from the first set can be matched up with in a meaningful way from the observations of the second. So I got myself a little example here. All right, physical therapists have various exercises they use to treat patients after breaking an arm. Researchers want to test a specific exercise to see if it provides an increase in motion. Several patients recovering from broken arms are tested before the treatment exercise and after the treatment exercise for improvement. The range of motion for the pre and post treatments are plotted in the dot plots below. When using a two sample t-test for the differences of two means, that's what we just did in the last section. The test of the difference in the range of motion, they found that the exercise did not show significant difference with a t-value of negative 0.16 and a probability of 0.2. So here we'd say we'd failed to reject under the old system because the p-value is too high, it's not less than the 0.05, so that we would say they're about the same. The exercise didn't help. All right, so here's what the plot looks like, right? In this chart right there of those 2 points, and then this is the data you would get using the method. But this is only done if the sample is independent, and we already know that we're testing the same patient before the exercise and after, so this is a dependent sample, so we'd be using a paired t-test. And if you look at the paired t-test when plotted out, 1, 2, 3, 4, 5, 6 of the 7 patients showed increase in motion after the exercise. So even though the one sample said no, the paired t-test will probably say yes, but it's the most appropriate test to use. All right, so your pro tip here is distinction between paired and independent samples is an important one because the methods used are different. When comparing two sample means, be sure to consider how the samples were selected, independent or dependent. All right. Let's go to the next page here. All right, when are we going to use these? We're going to use the paired t-test when the samples are not independent and connected in some meaningful way. The process of a paired t-test, you first find the difference between the matches, then you do the test. So you're going to subtract them first as opposed to averaging them all and subtracting the averages. We're going to subtract each individual pair. And we're going to use this little thing that's going to be called X difference. So the X difference, XD here, is just X1 minus X2, where this is probably the pre or this is the post test or whatever you're trying to do. One of your two dependent samples, you're subtracting the pairs together and then giving a single value here. So you're going to convert the two samples into a one sample XD. Once you do that, the entire process is actually back to a one sample t-test from chapter 12. So your MD is equal to a hypothesized value or greater than, less than, or not equal to that hypothesized value. Your conditions are all about the n pairs of difference are random and representative. Do I need to talk about how they're independent? No, because they're probably not. Okay, so that's why we talk about them being independent, because you'd use a paired sample, it needs to be dependent. All right, n pair differences need to be greater than 30. So you don't talk about the pre-test being greater than 30 and the post-test. It just means the differences are all greater than 30. The test statistic is back to the one sample test statistic that we've seen in the past. And the degrees of freedom is back to something reasonable, n minus 1. And on the calculator, you're using a one sample t-test, even though this is a two sample paired test. So a little bit of plot twist here. All right, the author of the paper, Chimpanzees Are Indifferent to the Welfare of Unrelated Group Members, concluded that chimpanzees do not take advantage of opportunities to deliver benefits to individuals at no cost to themselves. This conclusion was based on data from a study in which chimpanzees were trained to use an apparatus that would deliver food just to themselves when one lever was pushed, and would deliver food to both themselves and another chimpanzee in an adjoining cage when another lever was pushed. After training, the chimps were observed when there was no chimp in the adjoining cage, and then when there was another chimp in the adjoining cage. So they're trying to train him in an apparatus, and the first test is this chimp where somebody was in the next door, and then one where there wasn't another chimp, or vice versa. It's dependent because it was always the same chimp being tested, just with somebody there or somebody not there. All right, the researcher hypothesized that if chimpanzees were motivated by welfare of other, they would choose the option that provided food to both chimpanzees more often when the chimp was in the adjoining cage. Data on the number of times feed both option was chosen out of 36 for the samples for the 7 chimpanzees. Approximate value from the graph in the paper were given in the accompanying table. Do you remember this example when we were doing population proportions? So we did do this one, and you can see that the same example could be, if worded correctly, can be a proportion and sometimes can be a means. So you got to know, what are they looking at here? And this was the mean number of times that they fed both options. And I think the last time was like, what is the proportion of the time they fed both? What was the average proportion? Or not the average proportion, but the proportion. So the same example, just one was numerical and one was categorical. Is there convincing evidence that the mean number of times the feed both option is selected is greater than another chimpanzee when another chimpanzee is present in the adjoining cage than when there's no chimpanzee in the cage? All right, so your null hypothesis here is going to be that MD is equal to 0. MD standing for mean difference. And lucky for us, they gave us the data already there. But if they didn't, you'd have to literally subtract each of these out and get these values. What's the alternative then? The mean difference is greater than 0. So we're talking about the mean difference here. And so if it's greater than 0, that means they're charitable. That means that on average, they're giving more to when the other chimp is present than when the other chimp is not present. All right, so like, oh, another chimp, I'll feed him too while I'm at it. Oh, if there's nobody there, I just need to feed myself. All right, so what does MD stand for? It's mean chimp minus mean non-chimp. Okay, where C is chimp and adjoining cage. And NC is chimp not in adjoining cage. And what does mu represent?
Difference in the mean number of times the charitable option is chosen.
Yeah. So it's the mean number of times the feed both. Option is selected. Not the mean difference, because this is the mean. I'm sorry, the mean difference is the, oh yeah. Mu is just the mean difference, but MD stands for, is defined by this. So mu's are just the,
Okay.
all right. For the method, this is just a paired t-test. No fancy name other than paired t-test. There's not a paired t-test for difference or samples or whatever. It's just paired t-test. It's kind of boring. We got some conditions to check. Okay, they're dependent samples, right? Okay. Does it say whether these are chimps or representative or random samples? Okay, so STEM does not say that the sample is representative. Okay. Proceed with caution. All right. Does it say that the sampling distribution of chimps is normal? No, it does not. So we got to plot it out. 0, 1, 2, 3. It's everybody's favorite thing to do. All right, so 2, 0, negative 2, 2, 1, 3, 0. Look at that, guys. Appears pretty symmetrical, doesn't it? Appears fairly. Okay, we're gonna have to do stat edit. And put our values in here, 2, 0, -2, 2, 1, 3, 0. Then when we go to stat test, we're just gonna go to number 2 here. They don't have a paired test. So you're just gonna have to know that a paired test is really just a one sample t-test. So I'm just gonna do the t-test right there. I'm gonna have to pick sample data, which is already there. So our mu here is still 0, L1, greater than. The hard part about this is you're gonna have to pick a different color here. What do you guys like navy or light blue? What do you think? Light, that's so pretty, okay. Then we'll go ahead and we'll hit calculate. So our t value here is 1.35, p value here is 0.112, and degrees of freedom. Oh, they don't tell us degrees of freedom. How do we figure this out? It's just 6, yeah, because 7 minus 1 is 6. Okay, you're back to that easy one to calculate. What are we going to do now? We're going to fail to reject here, right? So, since the p-value of 0.112 is greater than an alpha level of 0.05, we fail to reject the null. Therefore, we do not have evidence that the population, I'll get it this time, population mean number of times the feed both option is selected is greater than guess whatever it says up here. Is there convincing evidence the mean number of time the feed option is selected is greater than the other chimpanzees present in the adjoining cage than when known? Okay, so where are we at here? Greater than another chimpanzee is present in adjoining cage than when there is no chimp in the other cage. Okay. Make sure you put population and mean so we know that we're talking about the population and that particular statistic.